Hello, welcome to this video on integral properties. I'm going to go through about 6 of them. A lot of them are in your textbook. One is, I think, not in the textbook, but it's something I want to show you just to be aware of. And I'm not really going to take much time to prove them. Might give some short explanation, but honestly, if you really think about the integral as a Riemann sum, all of these properties should make perfect sense. If you just think about it, if you think about what the graph would look like, etc., you should be able to really prove these to yourself. And it would be a waste of time for me to go through all the formal proofs and whatnot. So I just want to get through the properties, show you all some practice using the properties, and then we'll just do some practice with just standard definite integrals. So the first property says integral from a to b of k times f of x, right, where k is a constant, right? You can probably guess what this property says. You can pull the constant out to the front. And if you remember our properties with derivatives and limits, we did the exact same thing. And it should be no surprise, right? If the integral is the opposite of the derivative, and the derivative can do something, chances are the integral should be able to do pretty much the same thing, right? So the constant goes out to the front, but notice how there's multiplication there, right? It's not being added, right? It's multiplication. The idea kind of is that the constant, originally it's inside of the Riemann sum, right? This sum of a bunch of numbers, but every single term has this constant k scaling each rectangle, right? And so you can just sort of undistribute it from the entire Riemann sum. So that's the first one. That's a really useful property. The second one you guys have actually already seen before. The integral from a to b of the function f of x dx equals negative of the integral b to a f of x dx. Now, what you guys already saw was that when you switch the bounds, right, so this integral compared to this integral, the sign of the answer changes, right? It either goes from positive to negative or negative to positive. And we kind of already explained why, right? So if a is less than b over here, the widths of each rectangle over here are positive, and the widths, right, of each rectangle over here are negative, whereas the heights are both the same, right? It's just the same function here and here. The heights haven't changed, but the widths have all flipped sign, right? And so we should expect these integrals to have opposite signed answers. That's property number 2. Property number 3, the integral from a to b f of x plus or minus g of x dx. So just keep in mind, right, all this means is that, we either are adding or subtracting, doesn't matter which one. This should be equal to the integral from a to b f of x dx plus or minus the integral a to b of g of x, right? This one, if you want to prove it to yourself, it might be helpful to draw the graphs, like of f of x, right? And then to draw the graph of g of x, right? Who knows what they look like? But the idea is this thing right here is taking the output of one function, the output of the other at the same coordinate, right? Like at 2, say this is at 2. And you would add those outputs, and then that would be the height of your rectangle. You can kind of see, right, like this rectangle in this Riemann sum, and this rectangle over here, that essentially the idea is, well, we could also just take the rectangles and just stack them on top of each other and calculate the area of this new bigger rectangle, right? So that would be doing the Riemann sum this way. It's a very short explanation of it. Again, you could probably, if you're still confused, just keep thinking about it later. Property number 4. The integral preserves inequality. Right? So what does that mean? So let's say f of x is less than or equal to g of x for all x's, well, let me not use math symbols, in the closed interval a to b, right? And they're continuous, right? We got to say that they're continuous, otherwise it may not hold. Continuous, continuous. Then also the integral of f of x dx from a to b is less than or equal to the integral a to b of g of x, right? So that might be useful if you're dealing with inequalities, but it doesn't come up too often, so I don't want to waste too much time on that. Number 5, this is one that pretty much all of you could probably figure out in about 10 seconds. The integral from a to a of any function is equal to 0. Again, I think that should be pretty straightforward, right? It's kind of like calculating the area with a width of 0, right? There is no area. The area is 0. And the last one, this one is called the triangle inequality. It doesn't come up too often, but every now and then it's useful to have in your back pocket. The triangle inequality says that the absolute value of the integral from a to b f of x dx is less than or equal to the integral from a to b of the absolute value of f of x. This one is a little bit harder to sort of prove to yourself, but again, if you draw the graphs of just some general function, right, like over here, you know, let's suppose that f looks sort of like this, right? So it's got some parts that are below the x-axis and above the x-axis, right? So this is f of x. What would the graph of the absolute value of f look like? Well, it's actually going to look very similar until we meet those portions where it crosses the x-axis. So we got a part right here, and then it flips up for that little dip from the previous graph, and then it would go on and do sort of the behavior it normally does. So it just makes any negative output positive, right? So this is the graph of the absolute value of f of x. And if you look at the area under the graph, the area under this graph is a greater number than the area under here because we have this negative signed area portion. Whereas over here, there is no negative signed area. It's all positive. So anyway, that's a short little mini proof, I guess. All right, let's see these properties in action, though. So let's suppose that the integral from a to b, we're not even going to specify the numbers, of f of x dx equals 13. And then let's suppose that the integral from a to b of g of x dx equals negative 3. This is something the AP likes to do a lot because the idea is you guys are going to get very comfortable finding antiderivatives and calculating number answers for functions. But what if you don't actually have the function, right? This guy and this guy. And on top of that, what if you have no idea even what the functions look like? There is no graph for these provided, right? What if all we know is that this integral equals this and this integral equals this? They can actually ask you questions with integrals of sort of combinations of these two functions and expect you to know the answer. So I'll give you some examples. Let's do this one. The integral from a to b of -2 times f of x. So they're expecting you, the only way to do this is to use the properties. That's the only way. There is no other way. We don't know anything about these functions. So what property should we use? Well, let's pull out that constant, right? And we get -2 times the integral a to b of f of x dx. And you just want to use a property until you're left with an integral that you know what the answer is, right? Like this is an integral, and we know that it equals 13. So what we're left with is -2 times 13, which is -26. Cool. Let's do another one. Let's do something even maybe a little bit trickier. The integral from a to b of 2f of x minus 3g of x dx. I'm going to show you all the steps here too, because we're actually going to need two properties here. So the first one we might try to do is we might try to split the integral up according to this minus sign, right? Because this is a function, and we have a minus in between. That was one of our properties. So the integral from a to b of 2f of x dx minus the integral from a to b of 3g of x dx. Right? That's how I would split it up. And then now we want to pull these constants out. Right there and there. Right? That 3 is going to multiply. The minus sign will stay there. The 3 will go to the front. That's a better way to say it. So we'll end up with 2 times the integral a to b f of x dx minus 3 times the integral a to b g of x dx. And now we finally have integrals we know how to deal with, right? We know this one is 13, and we know this one is -3. So we just substitute in. 2 times 13 minus 3 times -3. Cool. So that's 26 plus 9. And that's going to be 35. All right, cool. Let's do maybe another one. Let's do okay. Let me suppose that in this case we actually get a little bit more information. Let's suppose we actually do have at least some knowledge about the graph of these functions. So I'm going to do a quick graph of f of x. Let's suppose it looks something like this. This is f of x. Now I want to be true to sort of the integral value, right? So we're going to suppose, right, that, this is where a is, this is where b is, and we want to say that if the whole integral is equal to 13, let's suppose that this signed area is plus 17 and this signed area is minus 4, right? You don't really have a whole lot of information, but you do notice, right, that the integral from a to b would give you 13. The integral of g of x should give us -3. So let's suppose that the graph sort of looks like that. So let's say that we have a positive signed area here of 3, a negative signed area of -7, and then a positive signed area of 1, right? We're going to suppose that's g of x. Cool. What if I were to ask you, what is the integral from a to b of the absolute value of f of x dx. Now you might try to scroll back up. Oh, I've seen that before. That's over here. But we actually don't want to use sort of an inequality relationship. We actually can get the exact answer, because we should sort of know what this graph should look like, more or less, or how the integral sort of changes, right? So look at the graph. If I consider the graph of absolute value of f of x, what changes? Well, the plus 17 portion stays the same, and then this part just flips over and becomes a positive signed area of 4. So the actual integral equals 21, positive 21, which notice, right, how this is greater than or equal to integral a to b of f of x dx inside of an absolute value, right? Like that would give you 13. That was the 13 we had over here. Okay. What if I were to ask you, what is the integral from a to b of 2 times absolute value of g of x dx? Well, in this case, right, we'd be referencing that graph, but we'd also want to factor out the 2. Right, let's pull the 2 out. And then let's focus on, okay, what would this integral give me as an answer? The absolute value of g of x, all that would change is that this portion would flip like this. The others would stay the same, but now the signed area for the middle portion is positive 7. So we end up getting an answer of 11 for the integral. But notice, right, that 2 is still there. So we have 2 times 11, which is 22. Nice. So that's just something to be aware of, because these are the kind of tricks that the AP likes to pull. So you got to make sure that you know these properties, right? They're not going to be given to you. They're not on, you don't get a reference sheet for the AP test, just starting, right? But you do need to be aware of these properties, because they can ask questions where you have to use them. There's no other way. Now let's just do some basic integral practice, just so we can get more used to anti-differentiation and all that good stuff, right? Let's go from negative pi over 2 to pi over 2, and let's do sine of 2x dx. Right, what does that integral give us? So again, for definite integrals, right, we say that this is our lowercase f function. We want to find the antiderivative, the capital F function. The accumulation function is another name for it. The derivative of what? Right? The derivative of something equals sine of 2x. That you want to think backwards, right? So what is that something? Well, it looks like it should be negative 1/2 cosine of 2x. Now, if you don't see how I got that, remember, if we were to take the derivative, we would have times 2 coming out because of the chain rule, right? So the antiderivative should divide by 2. So it does the opposite. The other thing, too, is that the derivative of cosine gives a negative, right? I don't want to see a negative in front of that sign. So I put another one in front, right? So that when I take the derivative of it, I get 2 negative signs that cancel each other out. So the antiderivative is negative 1/2 cosine of 2x. Or it's only one antiderivative, right? There are infinitely many, but we just need to stick with the simplest one to do this integral. So now we do f, capital F, of pi over 2 minus capital F of negative pi over 2. Right? So what does this turn into? Negative 1/2 cosine of 2 times pi over 2 minus, right? And what I usually do is, for the capital F stuff, I usually put it in its own brackets, and then Notice how this minus sign stays there, right? And we get two minus signs. This is the most common mistake. Everyone forgets that there's a minus sign right here in addition to any other minus signs that are a part of the capital F sort of thing. And so often students will just forget about one of these. And then they'll get a completely wrong answer just because they missed a minus sign. So don't miss the minus sign. So get -1/2 cosine of 2 times -pi/2. And we end up with, well, let's see, -1/2 cosine of, looks like pi. And then we get +1/2 cosine of -pi. Okay. Let's see. Cosine of pi, you should know this, it's -1, right? What about cosine of -pi? Oh, well, that is also -1. You should know that too. Look at that. They cancel out. We get an answer of 0. Does that make sense? Actually, it makes perfect sense, right? Think about the original function. This is what we call an odd function. So when you plug in a negative number, it spits out, a negative answer. And then when you plug in the same positive version of that number, right? Notice how these are the same except for a minus sign. You'll get the positive version of the exact same output. Another way to say it is, the graph kind of looks like this, right? And all the positive area here cancels out perfectly with the negative area there. So that's the idea. Let's keep going. The integral from 0 to 3, 2x plus 3 dx. All right, what is the antiderivative? That's going to be x squared plus 3x. Now, here's another way you can write this. Let's do it this way. Instead of writing all this, right, what people often do is they'll find the antiderivative. So they go here to here. And then they'll put brackets. They'll put one bracket, right? This bracket means evaluated from 0 to 3. That's super important. That's literally what it means. Evaluated from 0 to 3. You're going to see this kind of stuff come up on the AP test too, but it's also just so much nicer to write than all of this stuff, right? You actually don't need to write all that. You just got to know what this means and use this symbol, and it's a lot quicker. So again, now let's actually plug in the numbers and just use the fundamental theorem. So plug in 3. I get 3 squared plus 3 times 3. And then over here, I get 0 squared plus 3 times 0. That's nice. This is 0. Over here, I get 9 plus 9, which is 18. Beautiful. Let's do another one. Rapid fire. Integral from 1 to 5 of x squared dx. So this is going to be, what is the antiderivative? It's going to be x cubed over 3. And then this is evaluated from 1 to 5. All right. Let's set up our parentheses, minus, right? Put the minus sign in between. And now let's plug in the 5. We have 5 cubed over 3 minus 1 cubed over 3. 5 cubed, that's 125. 1 cubed, that's 1. So we end up getting, looks like 124 over 3, and I do not think that is divisible by 3. So I'm fairly certain that this is the simplified fraction. Cool. Let's do another. I got 3 more. 1 to 3 And we're going to do negative x squared plus 4x plus 3 dx. All right? What is the antiderivative of all that mess, right? It's going to be negative x cubed over 3 plus, let's see, that's going to be 2x squared, and then plus 3x, right? That is our antiderivative, and we're going from 1 to 3. I guess I'll do this below. So put your parentheses, your minus in between. I always make them super big in case we get something like this. Now let's just plug in the 3, plug in the 1, right? We get negative 3 cubed over 3 plus 2 times 3 squared plus 3 times 3. Now we plug in the 1 minus, right? So we got 2 minuses here. I'm telling you guys, that is the biggest mistake people make. I mean, it is so simple to forget that there is a minus already here. And then you might have another one right there. Anyway. Oh, sorry, I plugged in 3. What am I doing? I'm plugging in 1 right now. All right, 2 times 1 squared plus 3 times 1. All right. What does this turn into? That's a lot of 3's. There's 3 3's there. 3 cubed, 27 divided by 3. That's negative 9. And then I get 9 times 2, 18, plus 9. Okay, so that's nice. These 9's cancel. And then I'll keep the minus sign here, and let's do the inside of this one. We get negative 1/3 plus 2 plus 3. Okay, this is going to be 18 minus, I'll just keep simplifying over here. We get 5 minus 1/3. That's 4 2/3, which is, let's see, 14 thirds. 14 thirds. All right. Let's put the 18 over 3. Let's 18 times 3 is that 54 over 3? 54 over 3 minus 14 over 3. That's going to be equal to 40 over 3, right? There we go. So sometimes they get a little tedious. Take a little bit of thinking, but all integrals can be done without a calculator, except for the functions that don't have an antiderivative, but that's for another time. Most functions we're going to see are going to have an antiderivative. Let's do 2 more. An integral from negative 2 to 2. This one's kind of a challenge question. So the function is going to be 2 minus the absolute value of x. So if you try to do this the way we've been doing it, the biggest question is, what is the antiderivative of that thing? Now, there kind of is an antiderivative, kind of, but it's a piecewise function because the absolute value has this sudden change in behavior the moment, the x becomes negative. So what might be more helpful actually to do is to graph whatever this function looks like. So let's see. Here's the xy plane. And let's just find some values, right? So I'll make some tick marks here. 1, 2, 3. If I plug in 0, right? If I plug in 0 in there, what do I get? Well, I get 2. If I plug in 1, I get 2 minus 1, which is 1. If I plug in 2, all right, plug in 2, I get 0. Okay, and actually, right, that's x to the power 1, so that should be exactly a linear relationship. Let me just draw a straight line, right? It'll go from the positive 2 on the y-axis to the positive 2 on the x. What if I plug in negative 1? Well, if I plug in negative 1, it changes to positive 1, and then I have 2 minus 1, which is 1. I get this point. If I plug in negative 2, it turns into positive 2, and I get 2 minus 2, which is 0. So actually, again, on the other side, I now have this other straight line, but with a different slope. And the integral is the area underneath. It's pretty cool. Now, I guess one question could be, well, if this is a right angle, maybe we could do, base, 1/2 base times height this way, but I wouldn't do it that way. It might not even be a right angle, who knows, right? Actually, why am I making this more convoluted? Let's just treat this as the base, right? We have a base of 4, and this as a height of 2. So this integral should be 1/2 base times height. That's going to be 4. So this one, it's so much easier to just think about the graph. I don't know if I have enough brain power left in me to actually show you guys what the antiderivative of that is. That's maybe for another time. But let's move on to one more challenge question. Let's do the integral from -7 to 7. This one's going to be a doozy. The square root of 49 minus x squared. This is the very last one we're going to do. Now, again, if you look at this and you spend a lot of time trying to find the antiderivative, you're going to have no luck, because actually, as far as the techniques you guys know, there's not really a way to find the antiderivative here. There are some techniques we'll learn later, like U substitution, that will help us do stuff like this, but for now, it's actually an integral you cannot do using the antiderivative sort of fundamental theorem of calculus way. So again, we have to go back to the graph. Now I know if I plug in 7 or -7 in for x, I'm going to get a very nice answer of 0. So just notice, right, with these critical values, right, if I plug in those two numbers, I get an answer of 0. But also, if I plug in 0, I get an answer of 7. And hopefully you've seen something like that before. That's the equation of a semicircle. Right, so 1, 2, 3, 4, 5, 6, 7. Right, so we got a point here. 1, 2, 3, 4, 5, 6, 7. Point right there. 1, 2, 3, 4, 5, 6, 7. Point right there. And we've got a nice little semicircle going right there. And the integral, just like we know this, should be the area under the graph, right? So it is literally this green area. Well, we know how to calculate the area of a semicircle, right? A full circle would be pi r squared. So this would be pi 7 squared. But for half of the circle, we just take half of it. Easy peasy. Now for this answer, I would just leave it in terms of pi. In fact, for a lot of AP questions, you'll notice they actually like it if you leave your answer this way. It's just a cleaner, more exact answer. Don't want a messy decimal number. Let's just leave it like that. So anyway, I've gone on too long. Make sure you have those properties written down somewhere. They're very, very handy, and there are questions that ask you things that can only be done using those properties. So I hope you learned something. I hope you got a little bit more integral practice. We're going to be doing this from now until the very end of the year. We're going to be doing integrals every day, all day. You know, can't stop us. So anyway, have a good day. Should be some homework posted. And hopefully I'll see you guys, I guess, when I come back from retreat.